this particular problem, we have a block of 1.2 kilogram. It is stretched to the, or pull to the right here, a distance of 5.2 centimeters. The spring constant is 780 newtons per meter. If you need to pause, read on that, keep up. So the first thing I want to point out is that the distance pull here is given in centimeters, so make sure you convert that to meters so that it matches with the unit for the spring constant, because it is in newtons per meter. Okay, so let's go ahead and crack out A and B. To do part A, it asks us to find the acceleration the instant the block is released. So the moment the block is released, it is at a maximum distance to the right of 5.2 centimeters, which is 0.052 meters. So I think the easiest way to do part A is just set up Newton's second law and then just set up the net force being the spring force, because once you let it go, your hand is no longer touching it. So the only force acting on the block here is just the force due to the spring. So Fs here, S for spring, and then according to Hooke's law, the force for the spring is given as negative kx. And then to solve for A, I would go ahead and divide both sides by m. So as you can see here, everything is given to you. K is given to you at 780 newtons per meter. X here is 0.052 meters. So make sure you convert once again centimeters to meters. And then mass here is 1.2 kilograms. So once I do that, once I plug all my values in, really it's just a plug and chug problem. So if you do that correctly, you should get about negative 33.8 meters per second square. And it says here the acceleration, it didn't use the word magnitude. So since the word or the phrase here is pull initially, so pull in this case would be implying that it's stretching the spring to the right. So the moment you let it go, the block will accelerate leftward. So I will keep the negative sign in my answer. And so the answer right here would be negative 33.8 meters per second square. Now the other way to do it though, based on the phrasing of question or part A here, excuse me, is that it says the acceleration the instant it's released. So I know that according to Hooke's law, the moment it's released, that is when maximum acceleration occurs because it is stretched the most. So I can just use the A max function. So hopefully you're familiar with your harmonics function at this point. If not, hopefully you can look this stuff up if you like, or just prove it. A max here is given as A for amplitude and the angular frequency square. This resembles A centripetal equals R omega square if you did planetary stuff or centripetal stuff. All right, so here I know what A is. A is 0.052 meters, which is given the problem. What I don't know is omega square. Omega was not given. The angular frequency was not directly given in the wording. However, what I can do is I can set up conservation of mechanical energy or conservation of energy here to find omega square. Okay, so I can make a statement that's true. I can say that the maximum potential energy in the spring, which is 1/2 Ka squared, A being the amplitude, and that's stretched to the right or compressed to the left, that's going to generate the maximum kinetic energy because all of the Pe will be converted to Ke at equilibrium. Here, the 1/2 is going to cancel out. So to solve for omega square though, you notice here in conservation energy, the omega square term is not in there. But you do, once again, you do have to recognize that V max is simply A times the angular frequency. So the bridge function is that V is equal to R omega, but R is now replaced with A because we're using V max. So R would just be A because that is the maximum distance stretch or compress in a spring. All right, so V max by definition is just A times omega. I want to put that in parentheses. I want to square that. So this is what it looks like. So I'm going to go ahead and distribute the exponents squared to both A and omega. So as you can see here on both sides, there is an A square and an A square. So I'm just going to go and cancel that out just to simplify things a little bit. So to get omega square by itself, all right, ultimately to use A max, I need A, which is for amplitude, times the angular frequency square. Here I have angular frequency square. So really to get it by itself, divide both sides by m. So I can say that omega square is equal to K over m. So wherever omega square is, I can just substitute that in. So I'm just going to carry this first line down. So as you can see, A amplitude gets remains the same, just it gets carried down. But omega square itself can be substituted out for K over m. But I do want to point out, I'm not going to plug in my any calculator work here. If you look on the left side, it resembles what this particular function is, right? Where I'm circling back and forth. I understand that this function here has a negative, but really the second strategy here I'm trying to help you out is just to find the magnitude of the acceleration, right? So if you can see, well, K is on the numerator, K is on the numerator there. I know the left side has an x here, but really x is a because I plugged in 0.052, which represents the amplitude. So x is pretty generic, and x here is just equal to a because it's the maximum acceleration. And then the denominator is m, which is 1.2. So I can see here that the function I derive here in the second alternative method really ends up being the same as if you were to set up Newton's second law and set up the force being just the force of the spring. Okay, so a times k divided by m, which is pretty much the same as kx over m. All right, that's just to help you find the magnitude. All right, pick a strategy. Hopefully one of those makes sense to you. Let's do part B. Part B asks you to find the potential energy stored when it is 5.2 centimeters from the equilibrium. At 5.2, it is the maximum distance stretch. So I'm just going to go ahead and use PE spring. PE here is just 1/2 kx squared. So this is generic. However, I'm going to go ahead and replace x here with 0.052 meters. And then everything else given. So k is given. And don't forget to square your x term. And if you plug that in your calculator, you should get about 1.05 joules. Okay, so hopefully my calculator work is not off here. It is late at night. And then let's do C and D. C is just find the speed of the block as it passes through the equilibrium. So here's the key phrasing. It says equilibrium. So essentially what I can do is I can just set up conservation of mechanical energy or conservation energy here. I can say that all of the energy stored in the spring, which is PE max, will all be converted to KE max because it says equilibrium. So I know at the equilibrium, the spring is no longer compressed or stretched. So all of the energy stored in the spring will be converted all to KE. Okay. So therefore, I can just expand this. This would just be 1/2 Ka squared. So generically, it's 1/2 Kx squared, but x is now a because it's the maximum. And then, generically, it's just 1/2 mv squared, but here v is v max because I'm using a on the left side. Capital A once again stands for the amplitude. So 1/2 cancels out. So to find the speed at the equilibrium, which is really v max, I can go ahead and divide both sides by m, and then to do that, I need to square root both sides because this is v max squared. So to get v max by itself, square root both sides, get rid of the exponent. And other than that, it's a plug and chug problem. 780 is the k value. Once again, a, the amplitude has been converted to meters, which is 0.052 meters. Don't forget the square, and then the mass on the bottom. So if you do all that correctly, it should come out to be about 1.33 meters per second. And that would just be the speed. It asks for speed, so I don't really need the direction. So all I know for sure is that when it reaches the equilibrium position, regardless whether it's moving left or right, the speed is maximum speed of 1.33 meters per second. Okay. All right, let's do part D. Part D asks us to find the speed of the block when it is at half of the amplitude. So xi over 2. So half the amplitude is 2.6 centimeters, but don't forget to convert that once again to meters. So here, to solve for D, I think the quickest way to solve for it is just doing conservation energy. I can say that the maximum potential energy stored in the spring will be converted to Ke and Pe. On the right side, you have two terms because they're not at extreme points, meaning at 2.6 centimeters, the block here is still moving, but it's still being stretched. So therefore, there's some energy stored in the spring still, but at the same time, because it's moving, it has to have a Ke. So I can say that PE max is 1/2 Ka squared. Once again, anytime you do PE max, your x really just turns into the amplitude because that's how far it's being stretched or compressed. On the right side, I have two terms because both these terms exist. It's moving, so it has to have a Ke, and it's still being stretched by a distance of 2.6 because it's halfway. All right, and that, as you can see, 1/2 cancels out. So to get, what is it? What was on speed? Just to get v squared by itself, or just to get v by itself, I'm going to go ahead and do algebra first. The next algebra step I'm going to do is move this kx squared to the left side to join Ka squared. So that's going to look like that. And then therefore, to get v squared by itself, I will divide both sides by m. So that's the next algebra step. And then to get v by itself, I need to take the square root because this is v squared. So to get v by itself, square root both sides. So here on the left side, you notice here you don't really have to. This is Ka squared minus Kx squared. You notice both these terms have a K, so I factored out the K. You don't have to though. You can just keep it as Ka squared minus Kx squared. It's up to you. But regardless, just make sure your calculator work is on point. So here in the numerator, I have K, parentheses, A squared minus X squared, and the denominator is M. So again, once again, I square root both sides just to get V by itself. And as you can see, everything is given to you. K is 780. The amplitude is given at 0.052, and then X here is given to us in the problem, or in part D here, is 2.6 centimeters, which I converted to meters, and then Make sure you square both these terms because both these terms are a squared minus x squared, and then the mass is given as 1.2. And if you plug all that in your calculator, you should get a value of about 1.148 meters per second. Okay, and that's the answer for part D. Now, I do want to point out Vmax here that I found. Again, hopefully I'm not goofing with my calculator work here. It's 1.33. Right, that's how fast it's moving at the equilibrium. A common misconception that folks might want to carry over is, well, they would find Vmax, and to find part D, they would just take Vmax divided by 2 because it's half the distance, which is an illegal move. That is not proper. That's so incorrect, okay? Why? Because it's not a linear function. So as the block is released, it accelerates at a non-constant rate. Your acceleration continually changes because x changes. So acceleration depends on x, and x changes, so therefore a always changes. So it doesn't change at a linear rate, so don't just take Vmax and divide it by 2. That is an illegal move, so do not goof on that. That's a trap setup for you. All right, let's do part E. Part E and F here. Part E is pretty straightforward. To find the period of the oscillation, I hope you're familiar once again with your harmonics by now. The quickest way I think is just use the period function that relates to m and k, because both these values are given. M is given, k is given. So t is simply 2 pi times the square root of m over k. And I'm just going to plug and chuck. M is 1.2, k is 780, and times that by 2 pi, and you should get about 0.246. Okay, so I round a little bit here, so I kept it 3 decimal places. All right, let's do part F. Part F asks us to find the angular frequency. I think the easiest way to find the angular frequency once you have part E is just, well, angular frequency is just 2 pi rad divided by the period. So 2 pi rad being 1 complete cycle, period being the time for 1 cycle. So once you have that, really it's just 2 pi divided by 0.246, which I got from part E. Okay, if you plug that in your calculator, you get about 25.5 rads per second, or hertz is fine. Okay, and then the second option to do part F is just to say, well, angular frequency is just the square root of k over m. Once again, if you haven't proved these functions, you should definitely take time to prove it, and once you have it, hopefully you can just apply it. All right, therefore I know what k is, which is 780. The mass is 1.2, and if you divide 780 by 1.2 and then square root that, you'll get about the same answer, 25.5 or 25.54 here. It doesn't really matter to me. Again, there's a bit of rounding error here. All right, other than that, as you can see, it turns out the same regardless of which strategy you use. All right, stay nerdy, don't be whack.